Okay, section 2.2 is frequency distributions, and as I said, you will want your calculator out for this. When working with large data sets, it's often helpful to organize and summarize data by constructing a table called a frequency distribution. And you guys have seen these before, you just may not be aware that they had a proper name and what they're called. Because computer software and calculators can generate frequency distributions, the details of constructing them are not as important as what they tell us about the data sets. I'm going to show you how you can construct them, but how to interpret information from them is really what I want to focus on. So a frequency distribution is also called a frequency table. It shows how a data set is partitioned among all the several categories or classes by listing all of the categories along with the frequency of the data. This is like whenever you have a table and you have some category here, and then you start keeping track of your count. So if we're going through, let's say I had a list of 100 students and I wanted to find the numbers of A's, B's, C's, D's, and F's, I would go down my roll sheet, and every time I had an A, I'd put a tick mark. If I had a B, I'd put a tick mark. So I would expect to see a distribution that looks something like this, where I have more B's and C's, a few A's, a few F's, maybe some D's, but I expect to see a distribution that looks somewhat like this if it were a typical class. This is an example of a frequency distribution, but instead of looking at these hash marks here, we're going to be looking at number summaries, count summaries. So here's an example of a table that shows the IQ scores of a group of people that had low lead exposure. These numbers that are highlighted in red right here are called the lower class limits. They're the smallest number that can actually belong to different classes, and the numbers over here on the right are the upper class limits. Notice there's no overlap. If this ends at 69, this next number cannot be 69 here, because if it were the same, then how would you know which row to put a score of 69 in? The class boundaries, this is, by the way, for quantitative data. We're not talking about categories here. We're talking about numbers that can be measured on, using the highest level of measurement, our ratio level of measurement, and measured on a continuum. The class boundaries here are going to be a point that is 1/2 unit to the left of this number and 1/2 unit to the right of this number. So 49.5 would be our lower class boundary here for this first group. 69.5 would be the upper class boundary. Well, where that boundary ends, the next class here begins at that point. So that if you were to draw a histogram, your bars would actually end up touching because of the class limits. They would go 1/2 unit to the left until the two bars touched. All right, so that's our class boundaries. It's a number that's halfway in between this gap. The gap, what I mean by gap, is this difference between the last lower class limit and the the last upper class limit and the next lower class limit. So there's a gap of 1 unit. So to fill in that gap, half of it goes above, half below, so that's why we did the difference of 0.5 right here. Class midpoints would be the number that is exactly halfway in between 50 and 69. How do you determine what number's halfway in between there? You take an average. If we were to add together 50 and 69 and divide that by 2, we end up with 59.5. It's the number that is in the middle here. The class midpoints are the middle value in each class. So the class midpoints are the values in the middle of the classes, and they can be found by taking the average of the two numbers, the lower class limit and the upper class limit. Class width now is how wide the class is. And you can find the class width by looking at the difference between consecutive lower class limits or the difference between consecutive upper class limits. 70 minus 50 is 20, and 89 minus 69 is 20. That means that the class width here would be 20. The reasons for constructing frequency distributions. Large data sets can easily be summarized looking at a frequency distribution. We can analyze the nature of the data, and we also have the basis for constructing important graphs such as histograms. In order to construct a frequency distribution, the first thing you want to do is determine the number of classes that you want to have. In the previous problem, or the previous example, how many classes did we have? We had 1, 2, 3, 4, 5 classes. So once you determine the number of classes, and typically at least 5, no more than 20, otherwise the data gets too cumbersome, you can always adjust your class width somewhere in there. So we're going to calculate the class width and always round up. So if your smallest value, data value, and your largest data value, if the difference between those numbers is, say, 98, let's say that we're going to have 100 then. 98 is close to 100, round up. Then we could have 5 classes. Suppose the difference between your maximum data value and your minimum data value is 98. Then what we would want to say is we would have a total distance or total range is 98. Let's use a range of 100, that's rounding up. And if we want 5 classes, then we take 100 and we divide it by 5, and that means we're going to end up with a class width of 20. Your starting point, you've got to start with the smallest data value or a convenient value below that. Let's say that our smallest data value was 3. Well, maybe I want to start my class width or my minimum value at 1 since I'm got a range of 100. And then I could go 1 to 20, and then I would go 21 to 40, 41 to 60, 61 to 80, and 81 to 100. Do you see how I came up with these numbers for my boundaries? Another option could have been to start at 0 if I would have had a 0 value. All right, but you want to make these class widths the same and have a convenient starting and stopping number. Usually multiples of 10 or 5 or 2 are nice numbers for us. And then what we do is we take each individual data value and we put a tally mark in the appropriate class, add the tally marks up to get the frequency. In a frequency table, we would then put our total data value here, our counts here, 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 and here. Now that's just for a plain old frequency distribution, the examples of which you saw previously. There's a special type of frequency distribution called a relative frequency distribution, where we take our frequency and we divide it by the total count and change that number to a percent, and that's called a relative frequency distribution. So the total count here for this particular problem would be what? 35 and 35 is 77, 78, it looks like. So to get this 2.6, what we did was we took the frequency 2 and we divided it by 78 and we changed that number to a percent. Turn it on and we have 2 divided by 78, and that gives us our 2.6%. To change this number to a percent, we would just move that decimal over 2 places to the right. All right, so if we change we add this column right here that's the percentage of data represented by that frequency, that's called a relative frequency distribution. In a cumulative frequency distribution, we would take the previous count and we would add it to the count that we have here. So for example, here I have a count of 2, the total is 2. To get to the 35, I take the frequency that I have here and add it to the one that I had before, and that gives me my new total. 33 and 2 is 35. Here I have 35, so I would add 35 and 35, and that gives me my new total of 70. So that I end up with, finally for the last number, my total count. We let the values or the totals accumulate in this cumulative frequency. Notice the sounds of the words. Accumulate, cumulative, that's what's happening. Using a frequency distribution to understand the data. In later chapters, there's going to be frequent reference to a data with a normal distribution. In a normal distribution, the data will be symmetric and bell-shaped. Have you guys heard of a normal curve before? That was a big deal when I was a student. It's like, well, you need to have a normal curve, or can we have a curve on our test? And my professor at Baylor would say, sure, as long as it's a normal curve, because grades should be distributed normally. In a normal distribution, he would take all of the test scores. If it was a normal curve, C would be the highest grade, or there would be more C's than any other grade. He would have so many A's, so many B's, so many C's, so many D's, and so many Fs. So it didn't matter really what you scored, it mattered where your score fell in the class. If you wanted an A, you had to score higher than everybody else in the class, because he would only give 1 or 2 A's. You needed your test score to be the highest in order to get an A. Doesn't seem fair, does it? It's like, well, if I earned an A, I need an A. Well, not if the professor's grading on a normal curve, because the distribution that he ends up with right here, the grade distribution, is going to be symmetric and bell-shaped. Symmetric means that in the middle, we could draw a line in the middle, and the left half here would match up with the right half here if you were to fold that graph in half along the line. That's what symmetric means. Bell-shaped just means that it's got this peak right here in the middle and it looks like an upside down bell. They don't make math teachers take art, so this is the best I can do with my bell. So the frequencies start low and increase. So we started low, we increase, and then we start decreasing again and end low. That's what the bell shape is. Gaps. The presence of gaps can show that we have data from 2 or more different populations. So for example, here's a frequency distribution. And notice we have a fairly high number of count here, and then we have a whole bunch of zeros right here. And then our distribution starts back up again. So doesn't it look like this could be 2 different populations? Look at what this graph represents. It's the weight of a penny measured in grams. Most of the pennies here were between 2.4 and 2.6, we'll say 2.59 grams. And then all of a sudden we have another class of pennies right here that weigh between 2.9 and 3.19 grams. A gram is a significant weight difference for a penny. Well, what do you think could be accounting for that? What it's made of. Pennies made before 1983 are 95% copper and 5% zinc. Pennies made after 1983 are 2.5% copper and 97.5% zinc. The copper pennies weigh more, don't they? So when we look and we measure the weight of the pennies, it was obvious that there was a gap here and that our data were coming from 2 different distributions, because we have a whole lot of spaces with 0 here. For example, if we were to graph this data on a histogram, on a histogram 1, 2, 3. So let's make this right here 10 and 20. And I have 1, 2, 3, 4, 5, 6, 7, 8 classes. 1, 2, 3, 4, 5, 6, 7, 8 classes. This first frequency would go up to 18, which is about right here, drawing my histogram. The second one would be at 19, which is about right there, the second class. Then I have a whole bunch of zeros, 1, 2, 3 zeros, and I pick back up again right here at 2, and then at 25 for the next class, and 8 for this class. So looking at this graph, it does look like there's 2 separate distributions here, doesn't there? Those are the kinds of things that hopefully you learn to observe.